Okay, so in this last video, we're just going to look at some examples of problems involving conservation of momentum. And so in the last video, we talked about the principle of conservation of momentum. We did some simple calculation problems, and we also talked about the four different types of collisions and their definitions. And so we talked about elastic collisions, inelastic collisions, perfectly inelastic collisions, which, remember, a perfectly inelastic collision is a special type of inelastic collision where the two objects stick together or somehow combine their mass. Um, and what I call a superelastic collision, or what's also sometimes known as an explosion collision, which is a collision, not necessarily actually things colliding with each other, but is at least an event where momentum is conserved, and in which the kinetic energy of the system increases. So, for example, when a bomb explodes, that is an example of what I might call a superelastic collision. Okay, and so in this video, we're just going to quickly look at some more examples involving conservation of momentum. Okay, and so first, I want to remind you that in a perfectly inelastic collision, by definition, a perfectly inelastic collision meets two criteria. Number one, because it's an inelastic collision, kinetic energy is lost, and usually that energy goes to like heat or deformation or sound or some combination of those. A perfectly inelastic collision is one in which not only do the objects lose kinetic energy, but also the two objects somehow combine their masses. And so what that means is that because the objects end up as a combined mass, after the collision, both objects have the same velocity. And so we can use that idea to solve problems involving perfectly inelastic collisions, as we will see in the next example. Okay, and so let's take a look at example 3. So example 3 says to solve the following problem and identify the type of collision. And it says a 1 kilogram dart moving horizontally at 10 meters per second makes impact and sticks to a piece of wood with a mass of 9 kilograms, which then slides across a friction-free surface. Now, why does the dart stick to the wood? I don't know. Maybe there was like some glue on the end of the dart. Maybe the dart is pointy and it just ended up embedded in the piece of wood. Either way, it sticks to the piece of wood. As soon as you see that, the first thing in your mind should be, hey, this is a collision, so momentum is conserved. And number two, if there's sticking involved, that means it's a perfectly inelastic collision. And so when we're starting our work, we start with our concept, which is a conservation of momentum equation. So I write that down. I expand this out, and so because it's a two-object problem, I'm going to have two terms. So this is M1V1I, M2V2I, and then on the right side, I have M1VF plus M2VF. Now, why did I not label it V1F and V2F? Okay, so here's the trick to doing perfectly inelastic collision problems. Because the objects stick together and combine their masses, they have the same final velocity, and so that's the key. Because they have the same final velocity, I don't need to call it V1F and V2F. I can just call it VF and have it be the same thing. All right, but if that's the case, then I can also like combine like terms, or you can think I can factor out a VF from this right side. And so I can also think of that as like M1 plus M2 times VF, where I've just factored out the VF. And then this is M1V1I plus M2V2I. And you can only do that with perfectly inelastic collisions. And so if you identify your variables, we have, let's see, mass 1. This is before the collision, and so this is going to be V1I. This is going to be mass 2. You can kind of infer from context that the piece of wood was not moving before it was shot. I mean, it doesn't say that explicitly, but it also doesn't say that it is moving. And so I think we have to infer from context that the piece of wood was initially at rest. And so let's say V2I is 0, and we're asked the speed of the wood and the dart after the collision. And now we're solving for velocity, but if we just assume all this happens in the positive direction, then the speed and the velocity are basically going to be the same. Okay, and so if I plug into my conservation of momentum equation, I have 1 times 10 plus 9 times 0 equals the combined mass, which is 1 plus 9 times VF. I get 10 equals 10 VF. VF equals 1 meter per second. And that's it. Okay, simple conservation of momentum problem. And this also kind of shows you, by the way, the level of work I would expect you to show on this type of problem. Okay, so pause it there if you need to look at that some more. Okay, so perfectly inelastic collision problems are very common, as are what I call superelastic collisions. Now, the other types of collisions, those are like actual technical terms. Superelastic is basically something I use personally. I don't know if you would find it in a physics textbook like you would inelastic or perfectly inelastic. Those terms are in every physics textbook. Super elastic is, more something I say. So if you Google super elastic collision, you may or may not find something useful. But anyway, this type of collision, and I use collision in quotations because it might not actually be a collision, is one where the kinetic energy of the objects increase. Okay, and so a lot of the time when you're dealing with these problems, you're dealing with a situation in which the objects before the collision, and again, it's not really a collision necessarily, but it's some event in which there's no external forces and therefore momentum is conserved. And so you always have like some initial event or some initial condition and some final condition. Like, normally we would say before after the collision, but it's not necessarily a collision in this type of situation. Okay, so just to give you an example, here we have two ice skaters standing at rest on a frozen lake, and they push apart from each other. Okay, and skater 1 has a mass of 40 kilograms. I'm going to label that as M1, and is pushed away with a velocity of 3 meters per second. Okay, now when you go to label that, you have to think carefully about how am I going to label that, because your first instinct is going to be to say, well, okay, so it's going to be V1I. Okay, but it's actually not V1I because you have to think what is the initial condition of the two skaters? Well, initially the two skaters are just standing at rest on a frozen lake. So actually V1I is 0 and V2I is also 0. So what is that 3 meters per second? Well, that would be the velocity of skater 1 after they push apart. So that's actually V1F. And then we're given the mass of the other skater, which is m2. So in other words, I have conservation of momentum, right? The sum of the initial momenta is equal to the sum of the final momentum. When I go to expand this out, though, everything on the left side is going to be 0. Okay, because again, the event in this problem is the skaters pushing apart, and before they push apart, they're at rest. It says that in the problem. And so everything on the left side is going to be 0, which means that the total momentum of the system is 0. Now, does that mean that the momentum of skater 1 and skater 2 is 0? No, it just means that they add to be 0 because that was the initial momentum, right? And so on the right side, I have m1, which is 40. I have v1f, which is 3. And I can easily plug in mass 2, solve for v2f, and v2f is going to be -1 meter per second. Notice, by the way, that the velocity, first of all, is in the negative direction, right? And so when the skaters push apart, skater 1 goes in the positive direction, skater 2 goes in the negative direction. Skater 2 also has a lower speed because they have more mass. Okay, now this phenomena that I just described is what is commonly known as recoil. Okay, when two objects exert an equal and opposite force on each other, like the two skaters pushing apart, one of them goes in the positive direction, one of them goes in the negative direction. And it's the exact same phenomena that's responsible for the recoil of like a gun or a cannon or a rocket ship or something like that. Okay, now what type of collision is this? Well, you can probably figure out from context clues it's a superelastic collision because, well, I just talked about that on the last slide. But you can also go back to the definition. Remember, a superelastic collision is one in which the kinetic energy of the system increases after the collision. And the two skaters are initially at rest, which means their initial kinetic energy was 0. So EKI was 0. Now, normally I would go about calculating EKF, which I can do because I have enough information there. But to answer this second question, if I just want to know what type of collision it is, I don't need to do a calculation to know that this number is going to be more than 0. Okay, and so the kinetic energy of the system has definitely increased as a result of the collision. Okay, so pause there if you need to look at example 4 some more. Okay, so this example is one that I want you to try to do on your own. Okay, so number one, I want you to try to figure out what type of collision this is based off of the context clues. Um, and then number two, I want you to try to solve the question that's asking at what speed and what direction does the raft start to move. And it doesn't really matter which one of these you do first, of course. But notice something interesting about this problem. It's slightly challenging than the other ones we've done so far because if you pay close attention, there's actually 3 objects in this problem, not just 2 that we've seen before. If you understand the concept of conservation of momentum, it should not be difficult to extend conservation of momentum from 2 objects to 3 objects. Okay, so you should be able to do that if you understand the concepts that we've been talking about in the last 2 videos. So pause it here and try to do the rest of this problem on your own. Okay, so let's say we have mass 1, mass 2, and mass 3. How we label them isn't really important. From context, we can infer that everything is initially at rest because it says a stationary life raft. Um, and the 2 survivors dive off the raft at the same instant. The 55 kilogram person, which I called mass 2, goes south at 4.4 meters per second. Okay, so that means I'm going to label V2F negative 4.4 meters per second. And you might be saying, wait, why is it V2F and not V2I? Because V2I was 0. Because remember, there's always some event in these problems, and here the event is them jumping. Before they jump, they are stationary. So right there. And so V2I is going to be 0. That means V2F is negative 4.4 meters per second. And it's negative because let's say we use a normal coordinate system where north is a positive direction, and so south, the velocity would be negative. Okay, and then here we have V3F, which is going to be a positive 4.2 meters per second. Okay, so the question says at what speed and what direction does the raft start to move? Well, that means basically that we're looking for V1F. And this is a 3-object problem, but it's not a super difficult one. As long as you realize that because the initial situation is that everything is stationary, that means everything on the left side is going to be 0. Now you can expand that out if you want. It would be M1V1I plus M2V2I plus M3V3I, but all that is going to be 0. And then on the right side, I have M1V1F, which is my unknown, plus M2V2F plus M3V3F. Okay, everything on the left is going to be 0 because everything is initially stationary. And now it's just a matter of plugging in values. I have 160 V1F plus M2, which is 55, times V2F, which is negative 4.4, plus 72 times 4.2. And now it's just a matter of simple algebra to rearrange this and solve for V1F. Okay, and so I'm just going to grab my calculator really quickly. Let's see, 55 times 4.4, add that to the other side, and then subtract 72 times 4.2. Oops, 72 times 4.2 divided by 160. Okay, so V1F you should get is negative 0.38 meters per second, which means that the answer to the question is 0.38 meters per second and the direction is south. And this is a superelastic collision because in this type of collision, the initial kinetic energy of the system was 0, and therefore it increased as a result of this event. Okay, so pause there if you need to look at that some more. Okay, and then finally, here is example 5. I'm not going to talk all the way through example 5. You should be able to do this type of problem now based off of the last couple of examples we've done. And so I will I'll post the question and then you can read the solution on your own, but I'm not going to talk through the solution. Okay. Okay, so hopefully after watching this video, you fully understand how to solve conservation of momentum problems with all the different types of collisions. You have 3 different conservation of momentum worksheets that you can use for extra practice. That should be more than enough practice for sure. We are now done with this unit, and you should now be at the point where you can start preparing and studying for our unit test over momentum and impulse. As always, please let me know if you have any questions, and I'll see you guys in the next video.